In this video, we're going to expand the definition of a power of a point by including points that are inside of the circle. Suppose I take a point at random inside of the circle, and I take two lines that pass through this point, and they intersect the circle here, 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 and here. And then I denote these distances as x1 and y1 on one of the lines, and x2 and y2 on the other line. And the question is, what's the relationship between x1, x2, y1, and y2? The relationship will come after considering similar triangles. This triangle here and this triangle here are similar. Why? Well, because firstly, this angle equals this angle because we have two straight lines that intersect at this point. And secondly, this angle equals this angle because this is a cyclic quadrilateral and both angles point towards this side. So they correspond to this arc here. From the properties of similar triangles, we know that x1 divided by y2, which is the corresponding side in the other triangle, equals x2 divided by y1, the corresponding side in the other triangle. And so we get this relation. And it can be written as x1 y1 equals x2 y2. And because we chose these two lines at random, this means that if I chose another line, and I take x3 here, for example, and y3 here, then x3 times y3 will again be equal to this and to this. And so the value of this and this and this is intrinsic to this point and this circle. It doesn't depend on the line that we choose. And therefore we can define this to be the negative of the power of this point with respect to the circle. And we write it like this, where A is this point here and K is the circle. Now let's try to understand why we have a negative sign here, while when the point A was outside of the circle, such that in this situation, then this times this was defined as the positive power of the point. Well, it all comes down to understanding directed lengths. For example, take this segment here. I'm going to call its length positive if I count from this vertex to this vertex, and I'm going to call it negative if I count from this vertex to this vertex. And the rule is that always we're going to start counting the segments from the point A, and the second point is going to lie on the circle. And so here we have this times this, and because this direction is positive, then we have a positive number times a positive number, which is positive, so the power is positive. If we had chosen it to be otherwise, if we chose this to be the positive direction from this point to this point, then we would have a negative number times a negative number, which is again positive. So in both cases, we get a positive result. And if we look at here, again, we're starting from the point A, and the second point is always on the circle. And so x3 times y3. If we choose this direction to be the positive, then y3 would be positive, but x3 would be negative. So when we multiply them, we get a negative number. If we've chosen this direction to be the positive, then x3 would be positive, but y3 would be negative, and then the product x3 times y3 would be negative. And that's why we define the power to be negative in this case, and positive in this case. In a later video, we're going to see another justification for this negative sign here. But for now, let's consider what happens if the point A lies on the circle, or very close to the circle. Let's take this point A to be really close to the circle. And so I get this distance times this distance to be the power of A. But this distance here is really small, and so the whole power is very close to 0. Now suppose I took my point A here inside of the circle, but really close to the circle, then the power would be this small segment here times this here. And because this is very close to 0, the whole power is again really close to 0. And since the powers outside of the circle really close to the circle, and inside of the circle really close to the circle, both approach 0 when the point approaches the circle, then it makes sense to define the power of a point on the circle to be 0. And so, if I choose this point A to be on the circle, its power is going to be precisely 0. And this makes sense, because when the point is outside, it is positive. When the point is inside, the power is negative. And so when the point is on the circle, it is in the state between positive and negative, which is 0. Finally, let's prove that this quadrilateral is cyclic if we have that x1 times y1 equals x2 times y2. Of course, we're going to prove that this triangle is similar to this triangle, and we're going to use this relation. First, we're going to write it as x1 divided by x2 equals y2 divided by y1. And x1 divided by x2 is the ratio of the sides of this triangle at this angle, and y2 divided by y1 is again the ratio of the sides of this triangle that are at this angle. And because this angle equals this angle, therefore this triangle is similar to this triangle. And so we have that this angle, the angle against y1, equals this angle, which is the angle against the corresponding side, x2. And now because this angle equals this angle, we can conclude that this quadrilateral is cyclic. This is the optional problem. We have a triangle, and it's circumcircle. Then we chose a point on this side, random point here, and a random point on this side here. And finally, we define this to be the circumcircle of this triangle, and we define this red circle to be the circumcircle of this triangle. They intersect this line here and here. And we get these two intersections here, and we construct this segment and this segment, the green ones. We have to prove that they are equal. And here's the solution. Notice that the power of this point with respect to this circle is this times this, and the power of the same point with respect to the red circle is again this times this. And so this point has the same power with respect to the two circles. And therefore, this times this, which is the power with respect to this circle, equals this times this, which is the power with respect to the red circle. So if I mark the segments on this line as shown, then I can claim that b plus c times d, which is the power with respect to this circle, equals c times d plus e, which is the power with respect to this circle. We can make similar arguments for this point. Its power with respect to this circle is b times c plus d, and it equals this times this. And its power with respect to this circle is a plus b times c, and it also equals this times this. And therefore, a plus b times c equals b times c plus d. From the first equation here, c times d is going to cancel out with c times d, and we're going to be left with b times d equals c times e. From the second equation, the b times c is going to cancel out with b times c here, and then we're going to be left with a times c equals b times d. Hence, we get these two equalities. Now BD is both AC and CE, and therefore AC equals CE. Now we can cancel out the C, and we get A equals E, and so A here equals E here, as desired.